Welcome to the Thursday session of the R training. I'm so glad you're here. Yesterday, we made some of our very first plots with ggplot, and I heard from some of you that it's so much easier to use GraphPad Prism, and you're right. If you want to do something that GraphPad Prism knows how to do, it will certainly hold your hand through the process and get you from point A to point B. That's very good. They invest a lot of effort into making that software as usable as possible. And I frankly admire it. The people who use R and ggplot are trying for a specific result that they want to guide, and it is often easier to make an adjustment your PI requests of you for a figure in R than it would be in GraphPad Prism, because GraphPad Prism does it this particular way and may not make it very easy for you to edit. So I do think that the flexibility and customizability of R has a lot of value for us. Okay, will all of us use R daily? No. I don't even use R daily, but R has been a friend of mine since the early 2000s. And it's very useful to have in your back pocket as a tool for when you need it. All right, so this is Thursday. We are going to come back to this topic of missingness. We will not be doing imputation as part of this exercise. That's possible, but it's not part of what I've structured. I've really focused on graphical representation of data because I think that's kind of the best bang for your buck that I can spend this time on. But certainly there are many libraries available for doing imputation within R. Let's start by loading the ggplot library into memory because we're going to make use of that. So library ggplot2 should work on your laptop. If you weren't here yesterday, you may need to run install packages first. Does everybody have ggplot in place?
Yeah.
Okay, that's very good. Now, this next step is to read the transcripts table, and maybe that's going to work straight out, but I would remind you that you may need to see if it's actually there. In my case, I have not moved to the directory where the df transcripts file is found yet, so I need to go there. So I'm going to use the File menu and Change Directory to go to the right place. And it kind of remembers that I was there. Here we are. Select folder. Now when I say list files, I see df transcripts is right here. So that's good news. Is everybody able to take that step? I know that caused some problems yesterday, but I want to make sure everyone is able to change to the directory correctly. All right. And there's only one way to find out if it's really going to work. We're going to run this transcripts read table line, and you should get 2,860 rows and 19 columns. I did that with dim. I just said dim of transcripts. Use the dim function on transcripts, and that gave me 2,860 rows and 19 columns. Is everyone getting that? Good, good. All right, great. So that's the stressful part. Now that the computer knows where to find the file and has loaded it into RAM, the rest of this is cake. So that's good news. Great. Now, I would like to look at not all entries of transcripts, but just those that name a gene. So I'm going to use the next line. Named only is a subset of transcripts such that gene names are not equal to dot. What does that even mean? Let's take a quick look at this. I'm going to do at the top of transcripts $gene names. And I'm going to do say the first 100 values. Okay, so if you remember, the head function shows you the top of the file, basically. I think it defaults to the first 5 values. I'm passing it just the gene names, not the expression values, just the gene names from transcripts, and I've told it I want to see the first 100 values. Okay, so what this is telling us is that a large number of these rows of transcripts are only described as dot. Now that's a little weird, but in this case, they're using that approach to say, I believe to group together related transcripts that all relate to a particular gene. So we're going to screen out all of these dot lines and just keep those that have gene symbols. It may be helpful or not helpful, but we work in C. elegans worms in the Nolan laboratory. So one of the things I might want to do is screen out anything that was, say, CELE underscore whatever, genes that we don't know that much about, and just focus on stuff that we do care about very much. But in this case, it's a human data set. We're just going to focus on the stuff that isn't a dot. Okay. So so I've already run that command up here. That's right here, this subset line. So why don't we see what the effect of that looked like? Remember that we just ran dim transcripts and it showed us 2,860. So I'm going to repeat that command, but this time I'm going to pass it named only. Okay, that's a huge shrinkage. So in the original transcripts file, we had 19 columns. That is unchanged. But in the original file, we had 2,860 rows. Once we got rid of the stuff that didn't have an explicit gene name, we got down to 1,000 lines, 1,047. So that's pretty good news, right? We have much less data that we need to think about. We can focus on just those that have the best annotation available. I come back here. We're going to look at MA plots. MA plots are kind of an underused thing in gene expression, but they're very useful because in some cases, our technology can give better sensitivity in one experiment and then in another, and it might cause genes that have very low expression values to be much more likely to appear scaled up in one cohort and then down. If you have a pattern in which the intensity of signal for the gene is introducing a bias toward one cohort or another, you really need to know about that because you want to normalize that stuff away before it distorts the fold changes in p-values that you get. So MA plots are very good for that. I just wanted to say, if you're curious about why these plots are valuable, rather than listen to me, it would be much better for you to go to this paper because they go through a whole bunch of different visualizations for gene expression and explain why some of these are quite necessary as we prosecute our data. So it's a good thing to look at that. So in this case, we are going to pick a subset of columns by gender here. So I'm going to take a dim off that and dim off of male. All right, so what craziness happened here? We started with transcripts. We dropped down to just those rows with explicit gene names. Now we've provided 5, 6, 8, 9, 12, 14 and called that female for some reason. And we've chosen 3, 4, 7, 10, 13, 10, 11, and 13 male and passed that to male. This is a little weird, isn't it? So these are integers, but these can also be numbered names of columns, right? So in the original table, named only, I'm going to just give the list of names of columns here. Names named only. I had, as you recall, 19 fields up to Q value. When we look at these numbers, 5, 6, 8, 9, so we've got 1, 2, 3, 4, 5, 6. I wanted 5. Okay, so 5. So the number 5 corresponds to this column. The number 6 corresponds to this column. And then number 8 is down here. What we're doing is numbering which columns we want to extract from this table. So I have a vector containing these numbers, and I use the square brackets around it to say, these are the columns I wish to extract from named only, and put those into female. Similarly, I have these 6 columns that are numbered for males. You can see that if you put these lists together, you've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That refers to the physical order they show up in as columns in this table, which ones are male, which ones are female. So we're extracting out the data so that the female table includes just the female measurements, and the male's table, has just the male measurements drawn from the named only table. Is that clear? Started with transcripts, went to named only, then subdivided the expression data to male and female. Great. So that's a start. Now we have the data separated by cohorts, and I'm going to compute sums in female and male samples. So let's take a dim off of that, sum female. Okay, that's one. All right. Okay. So we've done something a little weird here. We've used a new function. This one's called row sums. Row sums is built into R, so it's not one we have to tell it what to do. Remember, I don't think I actually showed what these things look like. So let's show, I'm going to show what the top of the female table looks like. Okay, remember that here we grabbed out just the female columns to a new table called female, and here I'm showing you the first 5 rows of that. So those are the names of the FPKM values in the original table. These are intensity measurements for row 2, 7, 9, 11, and so on. Why aren't these rows 1, 2, 3, 4, 5? Because these are subsetted out of the original transcripts table. So the original numbers are what it's going to use to refer to these. So when I run row sums is going to compute a whole list of sums. It's going to compute the sum for this row independently of the sum for this row, independently for the sum of this row. We're going to do this because we're showing a magnitude to say what is the amount of signal for this gene across all samples. That's going to be how we make what's called this MA plot. So we need those row sums in order to give us the magnitude information. Oh, and I wanted to mention, I tried to do a dim on some female here, right here. So the female table up here has 6 different columns to it. But when I ran row sums, it no longer had dimension like this because it's just a vector. The sum for across all genes is just one-dimensional. It's not a table anymore because I've taken sums of each row. So when I ran dim on it, it gave back a null result. It doesn't report dimensions for one-dimensional vectors. So I can use the length function instead to simply ask how many sums came out of that. All right. Now, let us continue on. Now, I would like to know how many zeros are in these data. Zeros are kind of interesting to us because those represent missingness. Zeros. Okay. So in this case, there are some times when I have missing values in this expression table. Look at this top gene, for example. There were 6 females for which we made this measurement, and the first 3 have values, and the last 1 has values, but these 2 right here are reported as 0 intensity, or 0 FPKM values, basically. So these zeros tell us that there were no reads at all for this gene in this person. We can treat that as a measured 0, or we can treat it as a missing value. Does everyone understand the difference between a measured 0 and a missing value?
Yeah, one is the true biological information. The other is just missing.
Yeah, it's a difficult line in some technologies to draw. If I had fewer measured transcripts for one of these 6 samples than for another, I might find I had a lot of 0 measurements reported. It's just that that particular experiment was much less sensitive than the others. So in this case, I'm rather sensitive when I see something that says 0.0000. It suggests to me that this is actually a missing measurement than a 0. So for the purposes of of today, we're going to treat these as missing values. All right, so how do we get at those? I have this table of 6 columns and 1,000 rows. I want to know how many values in each row are 0. So what does that look like? Let's take a quick moment with that. Head, row, sums, female. Okay. So the logic on this one, I think, is a little tortured, and I'll try to walk you through this. What I'm producing, I'm adding together how many times I saw 0 measurements. I'm sorry, I can scoot that up higher on the screen so it's a little more visible. It's not very high, is it? There we go. Okay. So my row sums are not counting counts. They're counting absences. So when I just use female equals 0, remember that we're asking a question. Is this value, is this FPKM measurement for this person in this cohort 0? If so, the response is true. If it's a number, the result is a false. So what we're doing is counting how many times we had it's true, there's a 0 here. So this turns all of those values into trues and falses. Row sums then just says, each true is a 1. How many 1s did I have here? So correspondingly, the gene on row 2 has 2 missing values, right here and right here. The gene on row 7 has 0. The gene on row 9, 0. On row 11, 0. 13, 0. But once again, when we get down to row 22, we again have 2 missing values. So we should feel comfortable that the software is counting these zeros as missing values adequately across the rows. Okay. We still have a little bit left to go here, so let's look at these 2 log commands. All right. I'll help that up the screen a little bit. We want to know mean expression, which we're using with these row sums, and we want to evaluate fold change. These are the 2 main axes of an MA plot. We're going to have this magnitude that's going to be reflected by mean expression, and we're going to have fold change showing up on the other axis. So how do we get there? We started by computing a sum for how much signal was there among all the women and how much signal there was among all of the men. We're going to add those together and divide by 12. Why are we dividing by 12? Because there are 6 dudes and 6 women, basically. So we add those sums together, we divide them by 12, and then we take log base 10. Okay, so why are we taking log base 10 of these intensity values? Why not just show the values as the FPKM values look initially? We do this because of the extreme range of the FPKM measurements for these genes. Some of these have huge numbers of transcripts, and thus RNA-seq lights them up like a candle. But others are expressed so rarely and so lightly that they have very, very small magnitudes. We show intensities in gene expression and, frankly, in proteomics on a log scale because it helps us to put them all into one graph. Otherwise, you end up with a huge pile of stuff down near 0 and a sparse number of genes or proteins up at high intensities. Putting them on the log scale spreads it out better. Okay, next up, we need a fold change. So here we are going to compare the intensity from all the females to the intensity for all the males. Now, in a fold change, you're talking about a ratio, right? A fold change is usually like A over B or B over A, right? In this case, I've got a subtraction going on. So what is that? The answer is that when we look at differences in the log scale, we are looking at what ratios would be in linear scale. So if you take the log of something, you don't just divide it by something else. Division and log scale is no longer a ratio. Things just work differently in this way. So the way to compute a ratio when you're in log scale is to perform a subtraction. We take the log base 2 of female and we subtract the log base 2 of the male signal, and that's going to give us the full change in log scale. Is there more that I would really care to say about that? I think discussing how logs work may not be within scope for today. But if that math doesn't immediately make sense, I can try to explain it a little better. I will say that we look at differences on a log scale because we want them to be centered on 0, and a twofold swing in this direction or a twofold swing in that direction, we want them to be equally far away from the origin. So doing it on a log scale has a lot of back history in it. Why am I using log base 10 for intensity but log base 2 for fold change? Mostly tradition, honestly. You could put both of them on a natural log scale, and it would not change how the plot looks to a great extent. Having them on a log scale, however, does matter. What base you use doesn't matter tremendously.
Are we going to plot like a volcano plot after we all the
Volcano plots are tomorrow. Yeah, today is MA plots, but we will get there very soon. Okay. Now we've built all of these different vectors. We would really like to build them into a big data frame, because there are a lot of things that make plotting easier in a data frame. So let's make a data frame from it. Here I'm using the column bind function. So we have gene names. We want to retain those, quite obviously. We have the female measurements, which is to say 6 different expression values drawn from females, 6 different expression values drawn from males. We have the sum of all signals seen across the females, the sum of all signals seen across males. We have a count of zeros in the females and a count of zeros in the males. And we have the log base 10 mean expression, and we have the log base 2 fold change. All of that we want to staple together in a giant data frame. So that's been done now. I can simply say dim ma_df, and I see I still have 1,047 rows. Those are each gene on a different row. And I have 19 fields. It's quite a few. Let me see what happens if I say head of ma_df. These are the first 5 rows now. So I have my gene names showing up here. I have all the female measurements in a row, all the male measurements in a row. Some female is here, some male is here. Log base 2, oh, sorry, these are zeros here and here. And then finally down here we have the mean expression and the fold change. Quite often in an R project, you spend 90% of your time getting all the data crammed into one object that you want to display at once. And that's what we've done. We started with one data frame, the transcripts data frame. We subset it, we pulled the information out of it, and now we're putting it back in an order we can deal with a little more readily. So this is what we've done. So have we got a plot yet? No. Let's now ask just this first line here. This is a question. How many zeros do we have among the female measurements, right? So there are 6 females in the study. I am now asking for all of the missing values, how frequently were these showing up? So what I've done is to sort on the basis of zeros in each row. So right away we can see that there are nearly 600 genes that have no missing values. That's pretty comforting. This is this is not the only way to display missingness, but it is a useful one to just sort all the values by how many missing values there are. So yeah, loads of zeros here. That's brilliant because these have all the data points represented. We have a fair number of genes for which there's one missing measurement, a slightly smaller with two missing measurements, slightly smaller with three missing measurements. And of course, it is possible that you have only one measurement for a gene. Would it display a gene at all if it had all 6 zero measurements? It could, because you might have a measurement only in males and not in females, in which case these would all be zeros. But we see that the number of missing values is relatively small and shouldn't affect things very dramatically. We are going to explore a way to include that in our plots, though. Okay, I can also show how many zeros we have among the males. Okay. Does the situation look very different here? Not really. Yeah. So this is helpful. What if I want to make a table of that, though? If I wanted to show how frequently values are missing, I might try something like table MA. I'm sorry, I'm doing this from memory, so I might be doing it wrongly here. It's always nice when I remember the table function is really useful when you're trying to make a histogram for something. So in this case, if I give it all the zeros, the zero counts from the female measurements, I see that 576 had no missing values, and only 36 had all 6 missing values. So table is very useful when you're trying to just ask how frequent each of these values will be. Sorry, that one was actually missing from your script, but table is a very valuable function for that purpose. All right. Now let us, for our grand finale in missingness, compare the number of zeros in males and females together, looking across all of these genes. And here we see that we have, let's say, 550 samples in which neither males nor females had any zeros. And I don't know if that top value is an 11 or a 12, but we have a relatively small number of samples with a huge amount of missingness, or relatively small numbers of genes that have a very high degree of missingness. There's a fair amount missing here. I think we would agree. There's still plenty of zeros here that could cause problems for the statistics downstream. So now we have sort of a picture of what the missingness looks like. Let us do a quick MA plot using base R. So I'm going to run all 3 of these lines together. Okay. We can take a quick moment to glance at the figure that results. This is the spackle of dots that comes out of it. I'm going to talk about where it came from first, though. I could use the very long stick. Let's do this. All right. I love natural wood pointers. This is amazing. Look at this. Okay. All right. So we're using this really mega data frame that we put together. We're going to plot on the, oh gosh, this is a wheel. Sweet. Okay. On the x-axis, we're going to use the mean expression on log scale. On the y-axis, we're going to use the log base 2 fold change that we computed. Now, these fold changes are not changes between individual male and female samples. It's comparing the sums to the sums. So it's very much an aggregate fold change. All right. We're going to replace the label on the x-axis with log base 10 mean expression. We're going to change the label on the y-axis to log base 2 fold change. And above it, we're going to put a title bar that says differential expression MA plot something something. Right? So this is how you would do plotting in base R. A lot of programmers in R have given up on this altogether. They don't use the base R stuff, but I want to show you that it is still there available to you to use it. Now these next 2 lines are functions we haven't really talked about, but they're worth knowing. AB line allows you to give the equation of a line to be displayed on top of the plot. And here we want a line that is positioned at 1 on the y-axis and the other AB line is going to give us a line at the position -1 on the y-axis. Now let us look at the graph itself. Okay, so it's not glorious, but this is a scatter plot. What does each dot represent on this plot? Do we know how many dots there are here?
Thousands.
1071.
Okay. Yes, we know how big the table is. Each row of the table, that was 1074. Did I misremember the number? Well, it's however many rows there are in the big data frame we passed it.
47.
I got it backwards. 1047. Okay. So this is what 1047 dots look like. And each of these is going to represent some named gene in the original source table. What does it mean for a dot to be all the way at the extreme right? What does that tell us about that particular gene?
It's highly expressed.
Highly expressed, exactly. Yes. So we've got these on a log scale. So these dots are 10 to the 5th as intense as dots all the way back here. Right? So these are wildly intense genes, and these are boring little genes. So does anyone know how to spot the highest expression value in that table? You can sort the, you could say, use the max function on the MFDA object we created and say what was the highest value in the log 10 mean expression column. And it would tell you explicitly what number corresponds to this. So you could use this to say, what's the most intense gene? And is it actually as intense as it appears to be in this plot? Do I have a bug that's causing that point to be so far off to the right? I don't think we have a bug here, but yeah, it's just the case biologically that there's a huge space between the most intense and least intense in gene expression. Whether you're looking at messenger RNA or proteins, that's going to be true. So we have a huge dynamic range, but relatively few things occupying the top registers, and a pretty substantial number of genes right here in the mid-range. So between 1 and 3 on log base 10. Okay, great. Now, so if that is really hugely expressed stuff, this is the very least expressed stuff down here. What causes a gene to be high or low?
If it's different between male and female?
Yes. This is log base 2 fold change. So if it's way high, that's to say that in females, it's way high compared to what it is in males. And if it's down here, it's higher in males than in females. How did I get the orientation that way? Because we set up the log function that way. But we could have just changed the order of terms, and it would have been males over females rather than females over males. It doesn't really matter. They're just cohorts at this point. Okay, so things that are up here are changing a lot. Things that are down here are changing a lot. Where is stuff that isn't changing?
Between the lines?
Between the lines, brilliant, yes. So we put in a line that has position of 1 and another line that has a position of -1. How do we interpret positive or negative 1 on a log base 2 axis? See, sometimes biologists get a little weird when it comes to the log scale, so it's worth asking these questions. All right, it's cool. This line is where something would appear if it were double intensity in females than in males. This line is where, yeah, exactly. This is where it would appear if it's 2 times as high in males as in females, which is same thing as saying 1/2 on a fold change scale. But they're symmetric around the line 0, which means no difference between sexes. Okay, great. So this is an MA plot. It's got some limitations. Could we dress it up a little bit? Yes. We could use some colors to separate out the genes by some feature. But at the moment, this is a serviceable MA plot. Now, is it going to tell us something critical we needed to know from an MA plot? Why do we do MA plots? We do them because we're concerned there may be a bias towards one cohort or the other as a function of intensity. So, do we see values at very high intensity falling outside the expected symmetric range? All of these intense points are falling between the two lines. So that's pretty comforting to us. It says that when you have intense measurements, they don't have a strong penchant for being seen in women but not in men, or vice versa. That's a good sign.
But
What's that?
why? Biologically, why? It's important that the genes that are mostly expressed are not sex-related.
Yeah, I mean, we're all human beings, right? So,
Okay.
I mean, we all need ribosomes. We all need, pyruvate. We gotta do the same processes as human beings. So, what you're alluding to is actually a really important question. How much would you expect to change? So, if you're looking at something like gene expression in lung tissue of people who are longtime smokers and who have advanced cancers versus people who've never smoked and are maybe in the fittest years of their lives in their 20s or something like that. If you're drawing a comparison like that, you should expect large-scale differences, even though it's the same tissue, because these folks are having completely different phenotypes. In this case, there's not a huge change. So what we expect to see are differences, if I remember correctly, on X-linked genes, on genes that appear on X chromosome. I forget the rationale why. I need to reread that paper, frankly. But it's included with the data, so we can all do that. So it could be that you see something like an eyebrow, right? So maybe this is all along the same line, and then suddenly you see them all curved downward here. That would be a really worrying sign, because that means at low intensity, you have a very clear bias towards the male cohort. Or you could see, I guess, like an exponential fall, where you see a slope upward here, where you have a bias towards women at very low intensities. If you see stuff like that, you have a really big problem. You probably shouldn't go ahead and do your differential analysis, because until you get rid of that bias, that systematic bias, you're never going to find real differences. Most of your differences will be driven by the bias in the data. So the MA plot is a really important diagnostic. Do you see differences in fold change that respond to mean intensity? That's exactly why you would do this. Okay, but as I said, most people will not use the base R plotting functions to do this. So we should, if there are no more questions. Yes.
Can we, instead of narrowing the band between the two symmetrical values, expanding it depending on from which, like just to eliminate this bias of like capture more points at the very beginning, so that we reduce this bias.
Okay, so let's try. What is the interpretation of those lines I put on there?
The log 2.
Yeah,
Like
this is log 2 of 1, log 2 of minus 1. So is there a statistical interpretation of that? Honestly, the log base 2 fold change of at least 1 is not a statistical rule. It's a biological one.
it can be 5 and 5, and in this way we will include all the points that are outside, and we will get rid of the data that is.
Well, we're not at this time claiming anything is statistically different on the basis of this plot, right? We've gotten rid of all the variance here because we're just plotting a sum versus a sum. So we're not making a claim on this plot that all of these are hits. We're not doing it. We're showing those lines at 1 and minus 1 because there's a general rule among biologists that if you have a significant p-value, but your fold change isn't at least twofold one way or the other, it's just noise. the statisticians didn't make that. The biologists did. Because to statisticians, if you got a significant p-value, that's worth investigating. But biologists have said if it doesn't make a change of at least twofold one way or the other, it couldn't possibly be worth investigating. So these lines are in here as a guide to where the biologists would put that cutoff. But there's no p-value here, right? None of this is attached to a p-value at all. We'll get to that with the volcano plots tomorrow. Okay, now I would like to redo this, but this time we're going to do it in ggplot, because ggplot affords us a lot of variability that we can, a lot of flexibility, let's say. Okay, so I'm going to bring my console back up. Now, here at the bottom, I actually included the information on how to use the table function. So how many times do we see a 0 among the females or among the males in these measurements? So 576 have no missing values for females, 602 had no missing values for male. Great. So that's the more formal way to use table. Here I've specified that I want to treat the counts of zeros as a factor, but ultimately it makes no difference whether I include factor or not there. Okay, great. So I would like to look at cases where there are no zeros observed, where there are no positive values observed for males and females. Okay, so I've created that by subsetting the data by just those where there are 6 zeros for males or where there are 6 values for females. What am I going to do with that? Okay, so I'm going to do a quick dimension on those. Dim, no data male. Dim, no data female. Okay, so I had 27 rows for male where there were no expression values reported other than zeros, and there were 36 genes in which none of the females had any FPKN counts either. Okay, it's worthwhile knowing that because sometimes you have a lot of zeros reported. They may not be genes you want to keep considering. So down here, we can start with our ggplot. Now, I'm going to try to walk through the code a little bit, but let's start with the pretty picture. So we'll start with that. Here we go. We've run the code, and over here, now we have our magical plot. Let's talk about how we got there first. As you remember from yesterday, a ggplot has a lot of different pieces that all get stitched together. We have geometric shapes. Sorry, I scripted again. How are we doing on lunch, by the way?
Yeah, 10 minutes.
10 minutes. Oh my goodness, 10 minutes. Okay, keep me on target here. Okay, this is important. All right, we have a series of geoms that are going to show up here. These include the data points themselves, which are being represented as points. We have 2 horizontal lines that we're going to draw in here. That's part of, these are different layers that get added onto the image. And of course we have the input data, and we have the aesthetic. The aesthetic is to say, on the x-axis, sheesh, that really scraped something awful. The log base 10 mean expression. The y value, once again, is going to be the log base 2 fold change. But look, there's another element we're adding. Here, I've specified that the color that we use to create these dots is going to correspond to zeros female plus zeros male. So the color is going to indicate how many of these 12 were reported as zeros. All right, so we start with that base. We provide then the geoms that represent the data points, the lines that we want to use to help us interpret, and we're going to add a title element up at the top. So it's as close as I can get to making the same plot as we did before in base code, but this time we're adding in the color element to reveal the missingness. All right, so how did it turn out? Well, personally, I think that these fonts are a little small, and I'd kind of like to see what this looks like, maybe as an SVG that's sized better, so that we could see all the text here. But that's something that's getting fixed when we tell it how to export the graph, rather than how it appears here. I'm not going to worry too much about that. Now, we have two new elements I really think we should talk about. First off, what's all this business up here? See these little tick marks along the top?
Mm.
Okay, so we have a little popcorn on the ceiling, and down here, we have a little bit of grass down here at the very bottom of the graph. What do these represent? Did those show up in the earlier plot?
Mm.
No? No, they did not. Okay, but they show up here, so let's interpret them. What does it mean to be smack bang against the top of a graph or the bottom of a graph on a log base 2 fold change?
Are these the genes that are expressed only in one sector?
Brilliant. Well done. Yes. Yes. When you're computing the log base 2 ratio and the females have 0 expression and the males do have expression, I mean that ratio is not 1. It's way far away from that. It's an infinite ratio. And ggplot renders those by putting in this grass right here. So we can see that these genes all represent cases in which female expression was 0 and male expression was at least 1. On the other hand, it's possible that you have plenty of expression in females, but 0 in males. And in that case, you're going to fall all the way at the top of the graph. So already we see that there's a little bit more information showing up in the ggplot version of this graph than appeared in the base R version of the graph. The next thing that we can talk about is this missingness. Before, we didn't really have an easy way to convince base R to change the color of those dots to reflect how many zeros they contained. So we see that our scale runs up to probably like 11 and down to 1. Do you believe that missingness is randomly spread across the mean intensity axis? What would that look like? It would mean that you have the same mix of dark and light blue at every point along the x-axis. Do you think that's true?
No.
No. Okay, where do you think you find it? Where do you see the lightest values?
The smaller.
At the smaller end. Okay, and this comes directly to a point we were talking about in the lecture a moment ago. Blinking lights. Okay, it's not just me. It's been a week. So we see that we have more missing values, lower intensity values. That is to say, this is not missing completely at random. This is missing not at random, MNAR, which means when we impute values, we shouldn't just pick a random intensity. We should be aware that the missing values are concentrated in the lowest expressed genes. Okay, so this is a pretty informative MA plot. Maybe you want to include it in your lab notebook. So how do you go about doing that? We did this in ggplot, and we talked about it yesterday. We want to save this somehow. And so we're going to use the ggsave. Thank you very much. And that brings us to the very last line of the code for today. In fact, we're going to make your 10 minutes. This is good. All right. Well, we still have 7, I guess. All right. We're going to create a PDF. And we're going to specify that it is 14 centimeters wide, 12 centimeters high. I come up here to console, and I write it. So now I should see an MA PDF file. Here's mine. I'm going to just open it up in PDF Studio. Oh, look at that. All right, I'm going to fit it to page. Look at that. Okay, so what looks so different? It looks different because I gave it a pretty constrained size to fit within, and as a result, it expects that this should be legible at this size. So it has resized those fonts to reflect that. And I've got this inconveniently large legend sitting off to the right. If I were being very picky, I would probably tell R to throw this legend at the bottom, and then it wouldn't interfere so much with my mean intensity axis. I would also say that at this size, these individual genes are plotted pretty largely, which means you get some amount of overlap among them. It becomes harder to see kind of where the light blues are in here, but each light blue can be seen a lot more clearly because the dots are big. So maybe better, maybe not. I don't know. Oh my goodness, we just lost our projector. It's no good. It's that. All right. Well, I'm going to say nothing bad about the projector because we need it tomorrow. But here we see that we were able to create a graph that told us about missing values, told us about biases relating to the cohorts and the amount of intensity that we had. It's a pretty valuable QC, a quality control, to help us assess whether this gene expression experiment is satisfactory or not. What we see is that, ooh, that's a bad sign for tomorrow, that the biases in the data set seem to be pretty small, that most of the data are sitting right along the 0 fold change line where we expect them to be. This is part of differential expression experiments. We expect a baseline of no difference against which a few genes appear to be different. That's really the comforting way that most gene expression data should appear. Okay. And if that's everything from you guys, if you have any questions, I'm happy to answer them. But otherwise,
It's food time.
it's food time. Very well. So I'm going to turn off the recording and feel free to ask me questions if you've got them. And if not, I'll see you tomorrow morning at 9:30 when we talk about post-translational modifications, a subject near and dear to my heart.